of observifolds, and is based on trying to look at observables via deformation of the contour that's defining the path integral. So this is work that's reported in the two papers shown at the bottom here. And is also in my student Tej Kamwar's thesis, which is on the second row here. So what's the problem we're really trying to deal with? And it's a problem of signal to noise in extraction of physics results. And there are many areas of science in which this comes up. Today we're going to focus on calculations of observables in quantum field theory using Monte Carlo methods. And these are really generically beset by noise. So if I have some observable O, then it has an expectation value, which I'll denote via angle brackets. And it also has a variance, right, and an associated standard deviation. And if I look at the ratio of the signal, so this expectation value of O divided by the square root of the variance, then that defines how well I can follow how well I can determine that quantity using Monte Carlo methods. And a signal to noise problem is really when that signal to noise ratio decays exponentially in some extensive quantity. For example, the time defining some correlation function. So at the right, I've just put two examples of this signal to noise problem. So the first example is from 0+1 dimensional complex scalar field theory. So a very, very straightforward system. And the plot corresponds to the effective energies of charge Q states for various values of Q. And as you can see by the error bars here, as we go forward in the Euclidean time here, the error bars are growing, and they're actually growing exponentially fast. And this is really just because there is this signal to noise problem. Another thing you note is the error bars start deviating from the actual expected values, which are the red lines here. And this is another issue. Really the distribution of samples here can't be well represented by an error bar, but the growth of the uncertainty with time is clear. So the second example at the bottom is turning to QCD, and this is a calculation of the proton effective mass function in some particular discretization of QCD involving fermions, so something that's really of great phenomenological interest. And again, you can see that as we separate the source and sink in Euclidean time, the uncertainties grow. And if you look at how these error bars are growing, it's in fact exponential. So this is, as I said, a generic issue, and it's hampering many analyses. So in particular in QCD, pretty much every quantity we look at has this issue. So the proton mass, things like G-2, a piece of that calculation where there is an exponentially growing signal to noise problem. We can think about more complicated systems like nuclei, and there it's an even worse problem. So Parisi first and then Lepage really showed us how to think about this. So if I take some two-point correlation function, so defined by operators O1 and O2 separated in Euclidean time, then and so let's just take a particular example. So in the figure up at the top right, I'm choosing my operators to be interpolating operators that create and annihilate states with the quantum numbers of a nucleon. Okay. So given that correlation function, we can ask about the variance. And so if in particular, I know that on ensemble average, this correlation function is real. So I can ask about the variance of the real part of this correlation function. So the variance takes its standard definition And one of the terms, and the one that's really relevant here, is this term that's shown on the right-hand side of this equation, is that it's the expectation value of the absolute value squared of the correlation, of the operators defining the correlation function. So it involves operator 2 at time t times its complex conjugate or its Hermitian conjugate at time t, and then the same thing at time 0 for operator 1. So if I look at this correlation function, you can see that in a generic theory, so let's just focus on a bosonic theory first, the operator O2 times O2 dagger has the quantum numbers of the vacuum. So we have a operator that creates states with the quantum numbers of the vacuum and annihilates states with the quantum numbers of the vacuum at time 0 and t. And so that means between those two times, we have all states with those quantum numbers, including the vacuum state, propagating. And so when I look at this signal to noise ratio, so presumably we've chosen operators O1 and O2 that by themselves have some particular quantum numbers, for example, the nucleon. So the expectation value of this correlator is going to fall off exponentially with the ground state of those quantum numbers, which I'll just note by E here. But the variance is dominated by the vacuum, so it has no exponential decay. And so in fact, the signal to noise ratio is just going to fall off exponentially as the correlation function falls off. So you've got a falling expectation value being eventually defeated by a constant noise. And so this is something where we will then not be able to extract meaningful physics from Monte Carlo samples without exponentially large numbers of samples. So that's the case in the bosonic theory. Fermions are slightly different and in fact slightly improved. So if we go back to the figures on the right, so the variance correlator in the case of a nucleon, of our nucleon correlator is shown as the second figure. So I have a nucleon and an antinucleon interpolating operator at time 0 and the same at time t. But because we've integrated out the fermions, and when we do that, we get the propagators, which are just non-local functions of the gauge field. We actually have some non-local structure connecting us between 0 and t. However, that non-local structure really doesn't prohibit the growth of noise, because if you think about what operators that the n dagger operator can create, you should really think that there's a conserved fermion and anti-fermion number that's propagating across these diagrams. So the number of propagators doesn't go away, but the propagators can rearrange. And of course, they can rearrange themselves to make a 3-pion operator, or a contribution that has the mass of roughly 3 pions. And so that's much lighter than twice the nucleon mass. And so the variance correlation function here will fall off at late times like e to the minus 3 m pi t. And so when I look at my signal to noise ratio, which includes the signal, which is falling off like the mass of the proton, and the square root of the variance, then the whole signal to noise is falling off like e to the minus mn minus 3 halves m pi all times t. And this prefactor here of mm minus 3 halves m pi t is something that is strictly positive. You can prove this is positive, and it remains positive even if you look at theories other than QCD, if you change the number of colors, for example. And so you have this intrinsic problem that it just plagues calculations of anything involving baryons or even mesons other than the pion. So the plot at the bottom right is a study that we did about 10 years ago, where we actually looked at the effective mass of this signal to noise ratio. Okay, and so we did this for a range of different systems. The figure just shows this for the proton in red and for a diproton system in blue. And as you can see, asymptotically, these quantities are approaching the expected signal to noise mass. So this mm minus 3/2 m pi value for the proton. And if you play the same argument, you can easily see that for a diproton system, you just get another factor of 2 in that noise quantity. And eventually, both of these curves get to their Lepage expectation. Okay, so you can do a little bit more. So Mike Wagman and Martin Savage noted that, in fact, this signal to noise growth is not uniform in the correlation function. So if I write the correlation function in terms of a magnitude and a phase, I can look at the contributions to the effective mass, this case again for the nucleon, coming from the magnitude and coming from the phase separately. And if you look at the magnitude, you see that this is very well determined, even to late times. However, it asymptotes to a value that is not the proton mass in this case. Okay. The phase contribution is okay. It's well behaved for early times, but then you see that the uncertainties are blowing up, and they're blowing up exponentially, just like the whole correlation function is. So the whole growth of noise is really confined to the fluctuations of the phase. And if you take these two effective masses for the magnitude and the phase and add them up, you get the full effective mass. But the point here is really this breakdown of where the noise is going. So you can do more. So you can look at the statistical distributions of magnitudes and phases, and you can look at moments of these distributions. And one thing that you can see is that in the lower set of plots, this is the deuteron correlation function from NPL QCD collaboration data evaluated at various different times. And this is the probability of obtaining a particular value for that correlation, normalized to the average, to the mean of that correlation at that particular time. So the average of each of these plots is 1. And from the left to the right, we go from early times to late times. And as you can see, the distribution is changing quite markedly. So the yellow histogram. However, at every time we can model this distribution by a product of a log normal distribution, which is how we expect the magnitude to behave, and what's called a RAP normal distribution for the phase. And a RAP normal distribution is really a normal distribution where you've imposed periodicity. And so as opposed to falling off forever, it falls off until you have the periodic constraint. And if the fall off is slow enough, you essentially get a constant distribution. So the product of these two is able to describe what we see in our lattice QCD calculations. And it again highlights the importance of phase fluctuations in real world QCD correlation functions that we're interested in. So I'll come back to this later, because really what this tells us is that the goal of trying to improve our ways of doing sampling is to deal with this issue of phase fluctuations. Okay, so today we're going to talk about contour deformation as a way of trying to improve, provide improved ways of getting at physical quantities. And of course, observables in quantum field theories are defined via path integrals that integrate over a specified contour. So in a simple scalar field theory, we're just going to be integrating over the real values of the field at each point in space-time. Variances of observables contain pieces that are similarly defined as expectation values of products, other field products. So what happens if a contour is modified in those integrations? Well, if you have holomorphic observables, then via Cauchy's theorem, they're not changed. If I have a holomorphic observable, the variance is not going to be holomorphic because it contains this term that is the absolute value squared of the original fields defining the correlation function. And so because it's not holomorphic, under a contour deformation, it's not protected by Cauchy's theorem and it can change. So what we're going to try and do today is look for deformations where, by definition, for holomorphic observables, the observable is unchanged, but where the variance is reduced. And we're going to use machine learning technologies to try and optimize such a contour. So that's the basic goal. So let's start with a simple example, just to see how contour deformation really works. So let's consider a Gaussian action for 1 degree of freedom. So that has a partition function that is just integral of e to the minus x squared over 2. And observables are value of observable weighted by e to the minus x squared over 2. Okay, and in this case, of course, we can evaluate what the partition function is, and it's just square root of 2 pi. So if I take the average phase as an observable, you can easily see that this falls exponentially fast with k. So I just plug in O of x is e to the ikx, and then I do this Gaussian integral via completing the square, and this is just given by e to the minus k squared over 2. Okay, so let's think about the variance of what we should see if we try and do a Monte Carlo estimate of that quantity. Of course, we don't need to because we can do this integral exactly, but let's just play this as a game. So the variance contains these 3 terms shown here. The first one is the only one we want to worry about. So this is the absolute value squared of the observable. And the absolute value squared of e to the ikx is just 1. And so we just get a constant contribution here with a factor of 1/2. So if I then look at the signal to noise ratio for this quantity, I've got my expectation goes like e to the minus k squared, and my variance goes like 1, right? And so the whole signal to noise ratio goes like square root n, so the number of samples, e to the minus k squared over 2. And so what we should see if we try and do a Monte Carlo sample of this is that we will need an exponentially large number of samples n as we increase k in order to have a well-defined estimate. And in Tedger's thesis, he did exactly this problem. So I've taken figures from here. So the top figure just shows this the quantity that I'm trying to evaluate. So e to the minus 5x. Sorry, I'm just going to fix my screen so I can see the whole thing. Yeah. So this is a plot. The top is the plot of the integrand for our observable for k equals 5, and then the bottom corresponds to a Monte Carlo calculation of this integral. Okay. And so for various different values of k. And as you can see, as you go to large k, you get very large uncertainties. In fact, you see deviations from the exact value, which is the black line shown here. Okay. So how do we solve this via contour deformation? So the integrand is holomorphic. In fact, in this case, it's entire. And so by Cauchy's theorem, we're free to change the contour. There are no poles to worry about, so we can change it however we want. So there are many choices you can make. We're going to just make a very simple choice, which is to shift our variable from x to x plus ik. And so in the equations here, we just go through various steps. So we're going to move our contour from the real axis to integrating along the contour x plus ik. And then I'm going to do a change on the second line. We'll do a change of variables from z to x. Okay, so we're just going to insert that z is x plus ik here. Now, change of variables from integral dz to integral dx in principle has a Jacobian, but in this case, the Jacobian is 1, so there's no factor. So I get this integral of x e to the ik x plus ik, and then e to the minus x plus ik squared over 2. I can mess around with that a little bit. And the phases go away completely, and I'm just left with e to the minus k squared over 2 times e to the minus x squared over 2. The e to the minus k squared over 2 comes outside my integral, and then I'm just left with the partition function. With the partition function. So this really is just the expectation value of e to the minus k squared over 2, which of course doesn't depend on x, so I can bring it outside the integral, and I just get e to the minus k squared times the expectation value of 1, which of course has no noise. So there's no sign problem at all when I do this contour deformation. So of course other contours can only be worse than this, because this one is a perfect change. For example, if I only shifted the contour to x plus ik over 2, I'll still have a sign problem, a signal noise problem, but it won't be as bad. And again, if I shifted it to e to the 3 ik over 2, I'd have a better problem than I started with, but I'd still have a problem. Okay, so let's go back to field theory. So as I've said before, with our path integrals in quantum field theory are defined by integrals over field values at every point. Those field values define some manifold M. And if I do this with a lattice regulator, this path integral reduces to a very high dimensional integral over the variables that parameterize the field. And so here, if we just take a scalar field, it really is just an integral over the values of the field at each point, 1 through n. If it's something like QCD, where you're integrating over the gauge field, then there's a Jacobian to go from the Haar measure to the integral over the angles that we'll see will define our SU3 integrations. And so what we'll work through today is 3 cases. So U1 gauge theory in 1+1 dimensions, complex scalar field in 0+1 dimensions, and SUN gauge theory for n equals 2 and 3 in 1+1 dimensions. Okay, so first thing we need to talk about is Cauchy's theorem. And I'm sure everyone knows this, but we can just think about this in pictures. So if I have 2 contours gamma 1 and gamma 2, then if there are no poles in the region that they bound, then the integral over going around those 2 contours is going to be 0. And that means the value of the function integrated over each of those contours is equal, right? This is just a schematic picture of that theorem. So mostly we learn about this in 1 dimension, but it actually extends straightforwardly to higher dimensions. So a contour deformation going from manifold MA to manifold MB leaves the integral value unchanged if the combination of those 2 contours bounds a region in which the integrand is holomorphic. And so this idea of contour deformation is something we can apply in higher dimensions. And it has been applied in other contexts in lattice field theory in higher dimensions. So in particular, in trying to deal with sign problems at non-zero density, there's been a lot of work starting with papers thinking about Lefschetz thimbles. And there's been a recent review of this by Andrei Alexandru and company. And Andrei, of course, is in the audience. It's also been used to study real-time evolution. With a few papers have used this technique there. And I believe it's also been used to look at field theories with a non-zero theta term. Okay, so that means that we can think about using contour deformation when we have holomorphic integrands. So in fact, most observables that we're interested in, or at least that I'm interested in, correspond to holomorphic or even entire functions as their integrams. So the action is a polynomial in field variables. And so e to that is going to give us a measure that is holomorphic. And typically observables that we're interested in correspond to polynomials in the fields, right? Evaluated at various points. And even when we think about fermions, we integrate those out analytically and they give us a determinant of the Dirac operator. But the determinant of the Dirac operator is really just a very large, very high order polynomial of the fields. It involves the fields at every point, but it's polynomial. So the measure remains polynomial when you introduce fermions. And then if I think about my nucleon correlator that I started with, which is built out of quark propagators, these are of course the inverse of the Dirac operator. But these, again, are just very large polynomials of the gauge field. And so all of these quantities are things where these contour deformation methods can be used. Okay, so let's just go through the argument for field theories. So we start with some observable O defined over some manifold M. We're going to deform that manifold M to M twiddle and write this in terms of the coordinates u twiddle on that manifold. That u twiddle is just a map from the underlying manifold, the original manifold, to the deformed manifold, and so I can go back to the original integration variables u by introducing a Jacobian, right? And then just writing my u twiddle in terms of u's. Okay. Now, if you look at this second line here, you can see that because this is an integral over the original degrees of freedom on the original manifold, I can think about this as that there is a deformed observable Q. So I'm going to multiply by a combination. I'm going to put back in the original e to the minus s of u and remove the s of u twiddle by defining this into my observable. Okay? And I'm also absorbing the logarithm of the Jacobian into this S effective. And so I have a deformed observable Q that is a complicated object, but now I immediately see that the expectation value of my observable O is the same as the expectation value of this modified deformed observable Q. Okay. So if we think about the variance, so the variance of this deformed observable Q, it is non-holomorphic, just like the original, the variance of the original observable O was non-holomorphic. The first term in this expression is just real part squared, so it's not a holomorphic function. And it's possible that the variance of the real part of Q will be less than the variance of the real part of O for some particular choice of deformed manifold. It's also possible that the variance of Q will be worse, but we won't be trying to find those cases. If we can find a deformation that produces an observable that has a smaller variance, then we've reduced our signal to we've increased our signal to noise ratio. So if we can parameterize our manifold in some way with parameters omega, this is our deformed manifold, we can try and find the best manifold by doing gradient descent on those parameters with a gradient descent of the variance. Okay. And so this is something that you can go through, and you can see this is actually something that I can evaluate as an observable on the original set of field degrees of freedom. So if I have a sample of field degrees of an ensemble of fields that I've generated, I can do this optimization of my manifold using that original sample. I don't need to be regenerating fields. Okay. And this is one difference to with the use of contour deformation in the case of trying to solve sign problems, where you do have to do additional generation of field configurations. Okay, so what should we think about observafolds, about the contour deformations? And of course, there are many possibilities. And sometimes we can get guidance from physics. So in the toy model we talked about, we just did a simple shift. So that's something we're certainly going to consider. We can also have more complex position-dependent shifts where we just do a if I'm integrating originally over x, I define z of x is just x plus a phase, a complex part, an imaginary part that depends on x. And so this just corresponds to a vertical shift at every point of my contour. And I can also do more general things. But we won't need to do that for today. Okay, so in practice, what do? So we generate an ensemble of field configurations. We define a parameterization of the integration measure. We define a class of deformations we want to explore, and we perform a minimization, and in what we'll do later, mostly a gradient descent of a loss function that's related to the variance, and in particular could just be the variance. Okay, and if we're happy with how that's gone, then we can evaluate our learned modified observable on the original ensemble, and we get our physics out. If we're not happy, we can repeat these 3 steps in the middle. We can think about different parameterizations of the integration measure. We can think about different deformations, and having done that, we can re-optimize. So let's look at a simple example, and the simplest example is Abelian gauge theory in 1+1 dimension. So we can work with the Wilson action here, but I'm going to write it in terms of angles, which are the arguments of the plaquette variables rather than in terms of the plaquettes. So my e to the minus, my minus beta sum over plaquette plus plaquette daggers, I can write just in terms of cosine of the angle that's the argument of the plaquette. And the observables I'm going to think about are going to be Wilson loops of different areas. Okay. So those Wilson loops are just products of plaquettes, which we know these are going to end up giving us something that falls off with the area of the plaquette. So Roman A is the area, where the calligraphic A is the actual path defining our Wilson loop. And we're going to deform our contour. And in this case, this means taking our angular variables phi of x at each value of x, and we're going to do the simple deformation of just adding doing a vertical shift. So theta of x goes to theta twiddle of x, which is theta of x plus I delta of x. And in this simple model, I'm going to do something even simpler. I'm going to just do a 1 parameter shift. So I'm going to set every delta at each site to be the same, and just we'll have 1 parameter delta, which is defining our contour deformation. So the deformed observable in that case is this expression here, which I've called x. So it's Jacobian times this difference of action, e to the difference of actions, times the original product of fields, written now in terms of theta twiddle. So I can plug in my theta twiddles, and if you go through, you can see that you get the following expression. So in WA itself, the addition of the imaginary parts I delta on the product of the e to the I thetas at every point just gives us a e to the minus delta times the area of the loop. There's also delta dependence hidden inside the theta twiddle in the first action contribution here. Okay, and by choosing delta, and in principle, the imaginary part of that action evaluated for the deformed variables can cancel the phase of the observable WA. Okay, so there's two things that happen for this deformed contour. You get the suppression by e to the minus delta A, and you get a cancellation of the phase between the original observable and the modification piece. And so by choosing delta to be the right value, you can get this to match up, and you can see huge improvements. And going back to to the introduction, where we talked about that the problem really is of signal to noise really is a problem of phase, you can see that the way that we've solved this here is by exploiting that. So the plots at the right just show the improvement, and so let's just focus on the lower one. So this is the signal to noise of the improved observable, and in orange, and the signal to noise of the original observable in blue. And in fact, in this one plus one dimensional theory, we can pretty much calculate everything analytically, particularly when we set just this simple contour deformation. And in fact, there are curves under both of these data sets that show the exact values. And of course, the results come out correct, as they must, because this contour deformation didn't change the expectation, but also the signal to noise, we completely track what the expectation is, because we can evaluate the variance exactly as well. Okay, so moving on, that was kind of just a toy, because we just had this one parameter. So choosing the right value of it was just a very simple thing we could do by just sampling different values. We can do something more complicated. And so here I'm going to turn to complex scalar field theory in 0 plus 1 dimensions. And so I'm going to write that theory in terms of a field phi that depends only on the coordinate t. And I'll write that as a magnitude and a phase. So doing that, I can write my action in terms of these magnitude and phase variables in the following form. And this theory involves two parameters, a mass and a quartic coupling lambda. So then we need to think about what deformation we're going to take. So here again, we're going to deform our theta t to theta twiddle of t. And we're actually going to leave the magnitudes invariant, because we've seen that it's really the phase variables where the noise problem is hiding. It's also just easier to only deform some coordinates. So in this case, we're going to deform theta to theta twiddle using parameters delta 1, 2, and 3 at each site, and using some function f, which we've defined, which has one additional parameter c, and we're going to use the real values of the magnitudes of our field variables as the argument of those functions. Okay, so you can go through and work out what the deformed observable is in this case, and it's given here. And I'm going to take two deformations. One is going to be setting most of the parameters equal to 0. So the c and delta 2 and delta 3 at each time are going to be set to 0. And I'm going to set the delta 1 parameters, so the ones that don't come with this function f, so just a constant shift, I'm going to set those to be equal to t prime times delta. So I've got a phase that's increasing as I go across my observable. And then after I get to t, so I'm looking at a correlation function that is just a 2-point correlation function shown up at the top right. And after I get to extent t, then I'm going to stop the deformation because it won't influence anything anyway. Okay, so that's deformation 1, and that's really a 1-parameter deformation. Deformation 2 is that we look at this full expression for theta twiddle and treat it just as a 3L plus 1 parameter optimization. Okay. So we can look at the signal to noise for the 2-point function G, and this is shown in the bottom right. We've chosen some particular parameters; they don't matter. So the blue corresponds to the original signal to noise; it's falling off exponentially. The orange corresponds to this first deformation, which is the 1-parameter deformation, where we can really do this by hand. And then the green corresponds to the second deformation, where there's a 3L plus 1 parameter optimization that we need to do. And you can see that the 1-parameter optimization does better than the original observable, but the full 3L plus 1 dimensional optimization does better still. Okay. It hasn't solved the problem completely, but it's given us at least an order of magnitude or 2 over the original observable.
We just wanted to, yeah, sorry for the interruption. You have 5 minutes.
Yeah, sorry, I'm going a bit slow. So I'm probably not going to cover that much in the SUN case, but it's really the same story. So let me just go through it briefly. So our action is, well, we all know what the action of SUN gauge theory is. So then we need to think about the coordinates, right? So in our prescription, we have an action, an observable, a choice of coordinates to parameterize our integrations, and then a choice of path, a choice of contour deformation we're going to make. Right, so there are different ways you can parameterize SUN integrations. We use that was written down by Bronson in 1988, and this writes everything in terms of azimuthal and zenith angles, and the action and our relevant and the observables that we're interested in are holomorphic in those angles. So the azimuthal angles are identified at boundaries, but don't have to have the contour can deform the value at the boundary. Zenith angles, we need to preserve the endpoints at the boundary. So there's 2 different types of deformation we're going to be doing, azimuthal ones and zenith ones. Yeah, let me skip. So if you're given plaquettes, you can write this in terms of these azimuthal and zenith angles, and if you're given these angles, you can go back to the plaquettes. Okay. So we're going to do deformations of these, and so I'm just writing this down for SU2. So our deformations take 1 zenith angle theta and 2 azimuthal angles phi1 and phi2 at each point x in our 1 + 1 dimensional space-time. And we deform these by doing a shift of the variable in the complex direction, but that shift depends on the values of our fields. And what we do is we let it depend on the values for points y that are less than x. Okay, and this is because we want the Jacobian to be easy to calculate, and this will make our Jacobian triangular. So then we need some function that's defining the deformation. And so these are where the parameters come in. So the yellow guys here are all parameters. And we're basically doing a Fourier series expansion of what the deformation is. And let me not dwell on the details, but as you can see, there are lots and lots of parameters that are going to come into this. And so doing the optimization is going to be harder and harder. So again, we're going to look at Wilson loops. Technically, we're going to look at the 1-1 component of the untraced Wilson loop, but the expectation value of this is the same as the expectation value of the trace of the Wilson loop, so that's fine. And we need to do this with having fixed the gauge. But the reason to do this is that this allows for a deformation that can change phases easily. Okay, so we did studies in SU2 and SU3 for 3 different lattice spacings, where we fixed the string tension in units of the extent. We take in each case 32,000 decorrelated configurations generated using a factorized HMC. And to do our optimization, we use 320 configurations for training, 320 for validation, and then the rest for measurement. And just to flash some examples, this is what happens in SU2. And so this is the expectation value on the left and the variance on the right of the 1-1 component of the Wilson loop of area A. Okay, and the blue points correspond to the original calculation, and you can see the noise is growing exponentially in the area of this loop. And the green points correspond to our deformed observable. And you can see that this is controlled for much longer, for much larger loops. And looking at the variance, you can see that we have 4 orders of magnitude gain in variance in doing this deformation. Okay, so the path that is learned is kind of interesting in this case. So the plot here shows the parameters that are defining the simplest path deformation. And you see that one of the parameters, which is related to one of the azimuthal angles, has this ramp structure, and then the other one has a small but constant shift. These are not things that I think you would have guessed going into this problem, certainly not in the SU3 case. So we did this at 3 different lattice spacings. This plot shows the variance of the new observable, the variance of the old observable divided by the new observable for each of the lattice spacings. And as you can see, the improvement is pretty similar in each case. And in fact, differences here are really probably due to differences in the training and the optimization. So our deformation allowed us to do kind of a Fourier series expansion. So the original results just take the simplest case where we throw everything except the first term away, but we can also include higher terms, meaning there are more parameters. But in fact, this doesn't seem to improve things very much, if at all. This could be because it's just harder to find minima in this case, because there are a large number of parameters, but this is the results we have. We've also tried a different parameterization. This does worse, but it's definitely interesting to explore alternatives. Okay, SU3 is very similar. Let me just flash these results. They basically look the same, but let me move through them. So just very briefly to say something about how machine learning entered this. Really, we're just using machine learning tools. Basically, we've done stochastic gradient descent to optimize the parameters. So our loss function was given by the variance. The gradients, we use JAX to do the auto differentiation to evaluate this quickly. And we evaluate this stochastically using batches of training data. And the training is done with a schedule that reduces the step size that we're taking once the loss stops improving. And then eventually we stop the training once the step size has been reduced a couple of times. We did investigate using additional terms in a regularization, such as an L2 norm, but these really didn't seem to be needed and didn't make it work any better. So one thing that is interesting is that transfer learning is useful here. So we can use one observable to initialize the deformation for another observable. So think about taking an area A loop going to an area A+1 loop. The plots below show what happens if we initialize from no deformation on the left, right, for various different areas of our loops, versus on the right, if we initialize from the next smallest loop to do to give us a starting point for our training. So you can see that we get to a lower loss in almost all cases. And you should note that the horizontal scale is a factor of 4 smaller on the right. So we're getting to that point much quicker. So transfer learning here has been very effective in making this project work. So let me just conclude. So we've seen promising results in this contour deformation method for trying to improve signal noise properties of correlation functions for observables. There are a lot of further explorations we can do. So we can think about looking at different types of possible or practical deformations. So the Fourier basis that we chose doesn't seem to be particularly inefficient, either that or it's hard to train it. So we might think about other things. And for example, we could also think about using machine learning to actually define the deformation. Of course, we want to go to higher dimensions. So we want to do this for 3+1 dimensions in QCD, of course. So this requires working with links rather than plaquettes. And this is what we're working on right now in 2 dimensions. And we see pretty similar performance in the problem formulated with plaquettes versus the problem formulated with links. And so we're optimistic that we'll be able to take this and extend to higher dimensions. And of course, we need to think about extensions to fermionic theories. And if we can do that, then it's onward to QCD. Thanks.
Thank you, Will. Thanks a lot for the very nice and clear talk.
Great.
Yeah. Is there a question in the chat? No. Okay. Oh, okay. Yes, I can see. Tom, yes, go first.
Yes, can you hear me?
Yeah.
Yep.
Very nice talk, Will. I enjoyed it quite a lot. I had a couple questions. One was actually related to your statement about transfer learning. If I understood correctly, the optimization of your contour deformation, I thought that would be observable dependent. For each observable or different observable you do, you will have different optimization, and yet it doesn't seem to be completely independent, because you said transfer learning was actually useful here, or did I misunderstand? Can you comment on that?
No, that's right. So in principle, 2 observables will have completely different optimized contours, right? And in fact, our Wilson loops are different areas. We're actually optimizing over a different space of parameters, right? Because it's the variables, the parameters are associated with the variables inside the loop, defined by the loop, right? So as we make the area bigger, there are more parameters that are being optimized. So what we're transferring here is the common parameters, and then we're adding another parameter that we need to optimize, right? And so there's a re-optimization you have to do after that. But you can see from the right-hand plot here that additional optimization is very easy to do in some sense. And I think, the reason for that goes back to like these plots where so this is the SU3 version of these ramps. I don't know if you can see my pointer, but we have these ramp behaviors of certain parameters, right? And so as I change the size of a loop, the parameters are moving coherently in some way, right? And so that's what the transfer learning seems to be exploiting, I think.
I see. Thank you. And my second question is a little bit more speculative. It goes back to your motivation for the signal to noise degradation, basically Lepage's argument, and the standard example you showed was with the mass of the nucleon and the signal to noise decaying as mn minus 3/2 m pi. Presumably, when you apply your method to lattice QCD, this will reduce or improve the signal to noise. But I'm curious to know what the physical implication of that will be. Will, for example, 3n minus 3/2 m pi actually get smaller from a spectrum point of view with this method?
Yeah, so I mean, the signal to noise ratio, if this works, will definitely fall off less fast with time. But I don't think you want to think about this as doing something to the spectrum. So, and that's really because if I, oops, I didn't want to do that. If I go back to somewhere here, so this deformed observable is no longer something that is localized to my 2 times, right? And so you really shouldn't think about there being a spectral decomposition of this deformed observable, actually.
Okay. Okay.
So yeah, we're not modifying the pion. We're not doing something simple like modifying the pion mass, right?
Okay.
Yeah.
Okay. Thank you very much. Thanks.
Yep.
Okay. Any other question? So I can't see any further questions. So
Well,
let's.
I would love to ask one more question if no one else is going to ask.
Yeah. Go on.
Well, obviously I noticed that the type of deformations you chose had a trivial Jacobian, and I'm wondering, can you imagine having to move to other types of deformations where the Jacobian won't be so trivial in the future, and what would that entail?
I mean, the deformations we're looking at are certainly a subset of all possible deformations. And you're right, these are the ones that have the simple Jacobian. I think going to something with a non-trivial Jacobian is a step that you would want to take only with caution, and you probably want to make sure that the Jacobian evaluation is not as hard as it could be, right? So there are probably classes of deformations that have non-trivial but not particularly non-trivial Jacobians that you could explore. I mean, I know the work in doing optimization for manifolds for sign problems. I mean, Andre and company explicitly moved away from deformations that required Jacobians because it was too computation demanding to do anything, right? I think that's a true statement, right, Andre? But
agreed.
Yeah, so it's really just a question of cost, right? If it costs a lot but you gain more, then maybe you would do it. But, yeah.
Sure, but it's hard for me to imagine, a standard Jacobian is volume cube scaling without anything special. So that's somewhat prohibitive scaling. So
right.
Yeah. Okay. Thank you.
Yeah.
Okay, so let's thank Will again.
Sure. Thank you.